Now let's look at the next example. So this is the oxidation diagram for the metallic system. So for example, we have the iron chromium binary system, and then we're going to add oxygen to calculate the oxidation diagram of the iron chromium metals. So we're going to set up like this and select all, and then select the database. In this case, we're going to select packed PS, FT oxide for the oxide, packed PS for the gas phase, and then FS steel database for the alloys. So we're going to try this calculation. In the end, we're going to have this kind of phase diagram with a metallic composition here in the x-axis and y-axis as partial pressure of oxygen. And then we can see the what kind of phase can be formed at the different partial pressure and the composition range. Okay, so let's try this one. So if you open the phase diagram and then we're going to create a new actual calculation. So I'm not going to load the last system. So say no, say yes, and then new. It's the same as the new actual reaction. So the unit we want to use is the in gram. So for example, if you go to the mouse left click on top of this, the unit actually the view here, you'll have this kind of the pop-up menu. So we're going to use Celsius and ATM, or if you don't like it, you can use the bar, whatever, and or if you can use the Pascal. Okay, so any pressure is possible. And then energy is not very important in this case, so we'll just set up as joule. And then quantity, so the quantity of the iron chromium metal ratio in mole or in gram. So let's take in gram, for example, and say okay. And then go search the database. And in the database, as we said, gas phase O2 is can be taken from the packed PS database, and the FT oxide for all the oxide actual phases, and then FS steel database for the iron, chromium, FCC, BCC, liquid, and etc. All those kind of phase. Metallic phase can be from the FS steel database. And then say OK. And then now we are adding the component. So iron, chromium, and then oxygen. So in order to activate the PO2 as one of axis, you always have to add O2 like this. Then package will take O2 thermodynamic property. So the partial pressure of O2 can be set like this. If you add this one O, of course the O contain and O2 is O2 can be made from the mono oxygen here, but however in the axis setting, if you're using mono oxygen like this, we're going to use the partial pressure of the mono oxygen. So in the equilibrium program, whenever you add oxygen in any of the component, then you can use the actually oxygen. You can actually select the oxygen in the phase selection, and then you can click the oxygen, and you can set the activity of oxygen, or you can set the partial pressure of oxygen, and then do the thermodynamic calculation. However, in the phase diagram, you have to always add a component you want to use for the axis in this actually the input file, input component. Otherwise, you cannot activate that component as one of your axis. Okay, so you have to always use the proper the formula, chemical formula of the species you want to use in your x or y axis. Okay, so we say O2, and then click next. Then we have all these phases. So let's select all solution phase. Good. And then let's select all the solid phase. We don't need the liquid phase, as we said before, because liquid is part of the pure liquid or slag liquid. And then many people now here is confusing. Do I have to select the gas phase or not? If you select the gas phase, for example, mouse right click, then you can select all these gas phase will be selected as a part of your gas phase and say okay. But in the most of the calculation, when we do the PO2 with something, you don't have to select this gas phase because we are not producing the gas phase in the real calculation. We simply set the gas partial pressure, and then because we set the oxygen O2 as gas partial pressure will be changed automatically without really producing the gas phase on top of the metallic phase. Do you understand what I mean? So we just control the virtually what's the partial pressure of oxygen, and then we do the calculation what kind of phase can be formed at that virtually fixed partial pressure of oxygen. Okay, but if you really want to see the evaporation of the or formation of the some gas phase, then of course you have to select this gas phase because this gas phase will be part of your product in that case. But in this case, we are using just we are just actually controlling the partial pressure without really producing the gas phase. Then you don't have to select the gas phase here. Okay, so this is really bit confusing part. So most of the time when you do the thermodynamic calculation, you don't need this one unless you are really producing the gas phase as one of the product. Okay, and then you go to the variable, click the variable here. Then you have this window. So we are now going to set up the the, the x and y axis, for example. So in this case, we are using xy axis, but because this is three component system, so even you can use this triangle diagram if you like, but this is not what we want. So we are using only xy axis like this. And sometimes people asking, okay, xy step here, what's the meaning? And to say frankly, I don't know very well either. And this is just the by default 11 is okay, so you don't have to worry about this one. Okay, so at least we are using 11 kind of calculation in x and y axis, so don't worry about this one. So xy, and then composition here. So composition and the log activity. So when you set composition, it means mole fraction of something or weight fraction of something. That's the composition. Okay, and but we want to use the PO2 as one of the partial pressure. So log PO2. So A here is activity. However, in case of the gas phase, you can assume this is partial pressure too. So we are using this one, log 10A or RT log lna. RT lna is sometimes used. Sometimes we are using RT lone activity because this is similar to the kind of excess Gibbs energy. Okay, so and or Gibbs energy, whatever, partial Gibbs energy. So something like that. But when you need energy, kind of the unit for your y-axis, sometimes you are using this one. But in the most of the time, when you pick the partial pressure, you are using this one, log 10 activity, log 10 partial pressure. So we need one of the, so we have to use the one axis, one variable for this one, and then we have to set another variable for this one, because among the three, if you set the two, one of them is automatically determined. So once you do this, then you can click the next. Then you set the now temperature in this case. It's good, 1600 degrees Celsius as it is. And then now we can go here. So log activity as y-axis, and then activity of what? Activity of the ion, but in this case, activity of oxygen, and you need this one. And then that activity, where you are taking, so gas phase as O2 from packed PS. Well, in this case, oxygen is very important species in terms of the gas phase because many people using the oxygen to pick the something for the still calculation. So that's why we even add O2 actually in the FS still database. But this and this one is basically same data. But in order to actually make consistent, let's keep using the packed PS gas phase. So this is the one. And then we can say, for example, minus 20 to 0. Okay, so partial pressure of oxygen from minus 20 to the 0. And then now this would be the x-axis, and then x-axis we want to use, for example, this one as ion over this one, 0 to 1. So this is the chromium over the total is 0 to 1. Chromium mass fraction. And sometimes people asking, okay, is there any way we can use the weight percent directly? You can say that this is chromium mass fraction. Then if you multiply this one by 100, this will be chromium weight percent. Then you have to set this one also 0 to 100. So this is possible. 100 chromium over the total, so that it means 100 times chromium mass fraction, that's a weight percent, and from 0 to 100. Say okay, and then do the calculation. Then you'll have result like this. Okay, so now let's close this one. It's too busy. And then also close this one, close this one. So let's go back to our calculation result here. So you can see that now in the bottom, okay, I have liquid phase. And then this one is the BCC phase, and this one is the liquid plus phenol, and then all different phases. So you can select all of this one, phenol and etc., slag and all kind of things. So how to read this diagram? So this is coordinate. The temperature is 1600 degrees Celsius. And then you have to select what's actually the amount of your chromium. So 100 chromium, so this is basically weight percent, as I told you. So for example, 20% of the chromium at 1600 degrees Celsius at 10 to the minus 14 partial pressure, then we'll have liquid iron chromium metal. That's what it means. Okay, this liquid is different from slag. Slag is the oxide liquid, and liquid here is the metallic liquid. Okay, and then if you increase the partial pressure of oxygen above this one, now you can start to form the liquid plus chromium oxide, the corundum phase, M2O3. In this case, it will be mainly Cr2O3, of course. And then the liquid composition will be toluene on this side, and chromium composition will be toluene somewhere here. And if you want to, of course, check what's the composition, you can click this one, phase equilibrium mode, and then you can go, for example, here and click, and then mouse. Then you can see, okay, the partial pressure is this one, and the weight percent of the chromium is 50.77%. And under the condition, you have this gram of the liquid metal, and which is composed of the mainly this one. And then you'll have this amount of the chromium, so chromium oxide, 99% of chromium oxide, very small amount of Fe2O3 and chromium corundum phase. And this is 2 equivalent phase. So you can check in this way too. So this is the very simple diagram, metallic glacier, partial pressure of oxygen. Of course, you can do the similar thing, metallic glacier, partial pressure of S2, SO2, and whatever gas species you can use it here too. And you can do also multi-component phase diagram calculation like this. So you can set a multi-component system with a certain fixed actual composition, iron, chromium, aluminum, nickel, and etc. All the rest of them is the fixed value, and only changing the chromium amount. Then you can use it in this way, and then do the same calculation. Okay. Now let's just close it. No. Okay. So that's what we just did it. Okay. So now let's go to some other example. So this one, iron, chromium, oxygen, sulfur. So what we want to do is we want to calculate like this. So x-axis is partial pressure of S2, y-axis is partial pressure of oxygen. So this is kind of the stability diagram or predominance diagram. In the predominance diagram calculation, if you are considering every phase which is forming as a product here is the pure solid or pure liquid phase. When I say pure, this is not the solution phase. When it is stoichiometric phase, it's very easy to do the calculation. We have run those kinds of things in the even engineering thermodynamics. Probably some of you have done this kind of phase diagram for the pure iron, for example. And in the phase diagram module, you can include both pure stoichiometric species plus all the solid or liquid solution. That's the power of the phase diagram calculation for the predominance diagram. Okay. So how we do it? I mean, I'm not going to demonstrate for you, but you can understand easily. So iron, chromium, and then you have to now set the two gas species, O2 and S2 in the input. Then you can go here and you can select the, of course, database, FT oxide database, and the FS steel database and packed PS database. Sorry, packed 5.3 was the older database, but this is now replaced as packed PS database. Okay, and then you select only solid with all the solution phase here from the FS steel and the packed oxide database, FT oxide database, and then go next XY axis, and then the number of the composition for log activity equal to 2 because we want to use the both S2 and O2 as one of axis. So 2, and then we have the only composition variable is only 1, and then next you set the temperature, and then here you see that there's the oxygen partial pressure as a y-axis and from -20 to 0, and S2 as a partial pressure from 0 to -20, and then you fix the iron over the manganese over the iron manganese composition as 0.3, and then say okay. Then you can get this kind of phase diagram. Okay, and this is predominance diagram. As I mentioned before, in the phase diagram calculation, we are considering all the solid solution or liquid solution as well. So it's much accurate, more realistic kind of the phase diagram calculation. Okay. So now let's do the one calculation here now. So how about the iron, pure iron with partial pressure of oxygen, and then change the temperature? That's also one of possibility. So if you go back previous calculation, instead of the chromium, let's just remove the chromium. So then iron and oxygen, Fe oxygen. Okay. The unit here, because we are using only iron as our material, and then changing partial pressure of oxygen. So iron is not very actually important here, but anyway, we just leave the gram is not very important, but anyway, we just leave the gram as it is, iron, oxygen, and data, data search here again. Sorry, just click the wrong button. Database search, packed PS, FT oxide, FSD. Let's leave it as it is and say okay. And then go next. So even for the pure iron and oxygen, we have this kind of data can be used as the database here. And then you have the pure solid, and then no liquid and no gas phase, because all the solid liquid is here. And then covariable. And then here now we have XY axis and composition. No, I'm not going to change the composition because I'm using pure iron as input. And then I'm going to click this one as the log activities, because I'm going to use the log PO2 as one of axis, and then go next. And here now you can use this as x-axis temperature, for example, from 0 degree to 1600 degrees Celsius. Okay, and then this one, and log, this is as y-axis, log O2 as y-axis, minus 30 to 0, for example. So I basically, what I want to calculate is, I have pure iron, I'm changing the temperature from this one to this one, and also I'm changing the partial pressure of oxygen from this one to this one. What kind of the product will be produced from the pure iron? And say okay, and then click calculate. Then you have this calculation now going on. You see all this one? So this is the basically the oxidation diagram of the iron with a different temperature. So this y-axis is partial pressure of oxygen, x is temperature. So if I click this one, for example, you have Fe2O3 and spinel phase. Spinel is Fe3O4 in this case. And then this is monoxide. Monoxide is FeO, but not pure FeO, it's a solid solution. And here you have the FCC, PCC, FCC, and then you have PCC phase again, liquid metal, and the slag phase. You see all this one? So this is the, when you put the iron at the different temperature, different partial pressure, you can have this kind of the oxidation or reduction can happen depending on the partial pressure. Okay, so this is boundary at the given. So at 800 degrees Celsius, if you're higher than this one, you start forming iron oxide FeO from pure iron metal. So that's what it means. Okay, and you can do this kind of calculation for the very complex system. So for example, now let's close it. This is pure iron, but we can do the similar thing. So close this one, exit. No, we can do the similar thing here. So instead of iron, let's add a multi-system: iron, manganese, carbon, silicon, for example, and then O2. The database is exactly the same. So I wanna do the oxidation of the AA, the advanced high strength steel. Okay, so now go next. And then I select all the possible phase. Okay, and all the solid phase. That's good again. And then this one, and then go to the composition. So variable, at least I need the partial pressure of oxygen as one of variable, so then it will be 3. And then next, and then from, for example, 500 degree to the 1200 degree, I wanna know the oxidation inside of the furnace before it goes to the galvanizing, actually the process. So it's 500 to 1200 degree, and partial pressure of oxygen, for example, and then this is y variable, let's say minus 30 to minus 20. So I know the more or less answer where's the actual oxidation happening, so I just set up in this way. And then here, instead of this one, I say 100 manganese, and then manganese is 1.5%, for example. Is it okay? 100 mn over this one, so it's manganese weight percent in this case is gram. 100 times of the manganese ratio, weight, mass ratio or weight, mass fraction, so it's mass percent now, 1.5. And then I'll set this one as carbon, sorry, 100. I'll say this one 0.01, so 100 ppm, and then I'll go here silicon 100 and say 0.8%, for example. Okay, and then say okay, and then if you do the calculation, it's a very complex calculation, but however it's a very important, very practical calculation. They take a little bit longer time than usual, but you can see what kind of phase can be formed on the different partial pressure and then different temperature. So we have given steel alloys coming in, and if I treat this one at the given furnace temperature and under which partial pressure of oxygen, whether my steel can be oxidized or not oxidized, that's what we are calculating here. Okay, it's a very complex system because we have so many different oxide can be formed and also phase transformation over the metal as well. So here, let's look at it. So FCC, and this one, FCC plus BCC, and this is already oxidized, yeah. So it's BCC plus some oxide. So let's just change this one a little bit further. Sorry. So let's go outside, and let's change the partial pressure again. So go to the variable, mouse left click, go there. How about minus 40 to the minus 20? And say okay. Say okay. This one. So you can find actually this example in the one of the advanced example in the Paros application number 2 slide. But I want to just explain to you here how to do this kind of calculation, because this is practically in steel industry, this is very important. Okay, many things happening. So within the very, very low partial pressure of oxygen, there's something happening here. So let's go here now again. So this is BCC plus cementite because we have carbon. And then this is BCC plus FCC. So the two-phase region, dual phase region, and then this is FCC. And then in FCC, for example, at 800 degrees Celsius, we'll have BCC plus FCC two-phase region. And then if you go here now, you see that BCC, FCC plus rhodonite. And rhodonite is the MnSiO3 solid solution phase. So if you are higher than this partial pressure, I mean, if you put this steel in the furnace, and if you are controlling your partial pressure of oxygen by the dew point control, by using, for example, N2 plus H2 gas with some dew point control, and then at that dew point control, if the partial pressure of oxygen is about 10 to the minus 28, then you can prevent oxidation of the steel. You can only make BCC plus FCC. But if you are higher than that oxygen partial pressure, so if your dew point is higher, the dew point is higher than the proper dew point, you will start to form the oxide phase, rhodonite. And then if you're even higher, then you can have rhodonite plus SiO2. So you have the two kinds of solid oxide phase can be formed on top of your steel product. That's what it's showing. And of course, I mean, when you look at all this one, you have so many oxide is forming, and you may think all the iron is become oxidized. It's not. In the phase diagram, as I mentioned before, only for the binary and the ternary system, you can apply the the labor rule, binary or ternary labor rule. So you can more or less estimate what will be the amount of the each phase forming in each area. But unfortunately, if you go to this kind of multi-component system, even though there's a very, very, very small amount of the phases forming, you can actually show as the phase here. So it looks like it's a lot of the solid forming, a lot of rhodonite is forming, but in reality, it may be not very, not a lot. So you have to be actually be careful. So in order to check that, you can go to this phase equilibrium mode, and then go here, for example, at this point, and if I do the calculation under this condition, say OK, then you can see that this one, okay, 0.96 gram of PCC phase and 0.002, so 2.47 10 to the minus 2 gram of rhodonite, and then this amount of FCC. Even FCC is very small, yeah, and you can find this kind of information. Okay, so rhodonite, the MnSiO3, which is forming here, is not huge amount, it's a small amount. But however, if you look at now in your still PCC phase, for example, your manganese, so let's just check here, your Mn amount is only 0.46% remaining. Okay, so I'm adding 1.5%, and then a lot of manganese is actually consumed for the MnSiO3, so it can form MnSiO3. And of course, this is in equilibrium condition, but if you are doing very short time treatment, the formation of MnSiO3 would be much smaller than this equilibrium condition too. Okay, so this is the very simple actual phase diagram calculation. It's not simple phase diagram calculation, but very useful and very practical phase diagram calculation to understand the oxidation of the steel in the different grade of the steel. Okay, now let's go to some phase diagram calculation. So for example, let's make a new, say yes, yes. Now I want to actually show you the phase diagram calculation for the ion saturation condition. So for example, if you go to the blast furnace, so for example, this is the oldest calculation, but let's jump to this one. So if you go to the, no, not blast furnace, it's a BOF. You have the CaO, SiO2, and then FeO is the main system in the BOF. So basic oxygen furnace slag or converter slag in steel making is mainly CaO, SiO2, and FeO slag. And when you do the thermodynamic calculation for this kind of the FeO containing slag, you have to be a bit careful because as we learned in the equilibrium program, iron oxide, iron in this case, have the multiple oxidation state. Iron have the iron 2 plus, iron 3 plus oxidation state. So if you don't properly set up the calculation for this iron actually amount, iron 2 plus 3 plus amount, the fact says it cannot actually run the calculation for you. Okay, so for example, one of the way we can fix the amount of iron 2 plus and 3 plus is the set up partial pressure of oxygen, PO2. Okay, and the other way is we can add iron as activity equal to 1, or we can add small amount of the iron in the calculation with the slag, CaO, SiO2, and FeO slag, then it will make ion saturation by itself because there's the ion is existing in the system. Okay, so we have to decide. We can choose actually whatever we like. It's depending on case by case. Okay, so for example, in this case, let's look at this one. So for example, this is the iron oxide and silicon oxide binary phase diagram calculation, assuming the iron oxide, silicon oxide binary phase diagram calculation under ion saturation condition. So what we did is we are adding FeO and SiO2 plus iron here. Okay, and then we select all the phase. In this case, we select packed PS database and FT oxide database only. So FT oxide solid solution and all the solid phase. Typically, I say don't select the liquid phase here because this liquid phase can be already existing in this slag phase. But in case of the iron liquid may form. So that's why we go inside of the pure liquid and select only iron, Fe liquid. So Fe liquid like this way. So we click this one, go here, select ion, liquid. So we have ion from pure solid to the pure liquid, okay? And then click here variable, and then if you go next, then we are setting in this way. So here we have the number of component 2, and the partial pressure is 0 because we are not changing the activity in this case. And then go next, and then y-axis temperature 500 degree to 2000 degree temperature. And then in the composition variable here, now we put the ion silicon SiO2 of the Fe and Si 1, 1. So we make this third one as 0, to intentionally make it 0. So third one, denominator here, you have to make it 0. So 1 over this one, and then 1 or 0 to 1 for the x-axis, okay? And then the other one here we are setting is ion 1 over FeO and SiO2. Ion of FeO and SiO2. We set the very, very, very small amount of the Fe value here, 0.001 compared to the 1 gram of the system, okay? And we are intentionally basically adding ion metal in the calculation, and then say click and then do the calculation. Then we'll have this kind of result. So if you look at all the phase diagram here, there's always ion solid, and ion solid S1, S2, and then even ion liquid. So everywhere here we have the ion, but the amount of ion is 0.001 compared to the 1 gram of the total system. So we are in the ternary system calculation. We are in the Fe, SiO2, and ion 3 section, but so we have basically we have iron, silicon, and iron oxide, silicon oxide, and iron, but iron amount is very, very small. So we are projecting this one on, and then with a very small amount of iron, we did the calculation. So it means this should be very close to the FeO and SiO2 binary system. Okay, it's a nearly FeO SiO2 binary system, but there's the small amount of iron is always existing under the behind the ear. Okay, and so all this the oxide kind of type of phase diagram. This is basically oxide phase diagram with the ion in it. Okay, so all this line here, so slag plus monoxide, and then here is slag. Basically, if you remove all the metallic ion, then that will be phase diagram, which is nearly the same as the iron oxide SiO2 under activity of the Fe equal to 1. So it's ion saturation condition. So this is the most simplest way to do the ion saturation condition calculation. And there's the other way to do it, and we can, so for example, we can pick the partial pressure of oxygen, and we can set the very, very low partial pressure of oxygen, for example, if you like. And so we have FeO, SiO2, and O2, and then select all the possible phase, and then go here. Now one composition, one log partial pressure of activity, log partial pressure, and 1, and then temperature, and PO2, we set the low value, 10 to the minus 10, for example. This is reasonably low partial pressure, and then we set ion of this one, and then say OK. Then if you do the calculation, you see we thought this partial pressure is 10 to the minus 10. It's reasonably low, so it will be enough for the iron oxide and the SiO2 binary phase calculation, but the result here is quite different. So even 10 to the minus 10 atm partial pressure, we have Fe2O3 can be formed under this condition here at this temperature. Okay, so this is not low enough to preventing the FeO become Fe2O3. Okay, so this is not what we want. So because partial pressure of oxygen for the ion saturation condition at low temperature is very, very low, 10 to the minus 30, 10 to the minus 40 atm. So that's why if you're actually simply doing one partial pressure calculation, you may not actually get the result what you want. Okay, so it's not very good to use the oxygen partial pressure for ion saturation condition. But if you're actually doing only the ion saturation condition calculation or reducing condition calculation at the one fixed temperature, then you can set the reasonable partial pressure of oxygen and do the calculation. That will be very close to your ion saturation condition, because we know roughly what will be the partial pressure which is corresponding to the ion saturation condition. But otherwise, it's not very good actually, the method. Okay. And one other thing we can do it here is go back here. We do the same setting here, and then instead of the 2 and 1, we can set 1, 1 activity 1, 1, and then doing this one. And then we can set the activity of ion equal to 1. But in this case, you have to set which activity of ion you want to set. So ion of liquid activity equal to 1. In log scale, log activity of ion become 0. For example, then activity of ion equal to 1. Yeah? So you have to set either activity of ion equal to 1 for the solid or liquid. Okay. And then you can perform the calculation. Then you can get the very similar result like this too. Okay. So that's the third way to have this kind of ion saturation calculation. Okay. And of course, you can do also CO2 calculation and etc. So there's many different example here to do the thermodynamic calculation. But what I want to show you here is this one, CaO, FeO, SiO2 calculation under ion saturation condition. So as I mentioned, this is very important system for the converter slag and BOF slag. Okay. So how we do it? So we add this one. So we add SiO2, FeO, CaO with ion in it. And that means we're going to probably set the ion somehow. And then we select all the possible phase, FT oxide plus PECT-PS database, all of them. And then go here and set 3 actually composition variable and then fixed temperature, 1650 degrees Celsius. We set A, B, C axis, and then we just assign the ion as a very small amount. Then you can get this phase diagram, and then you can see everywhere you can see liquid ion is existing. But this is more or less in this on top of this ternary system. Okay. And then we can do the similar thing with even MgO, additional MgO conditions. So SiO2 and MgO plus ion. Okay. So the last one, MgO, this will be the constant value. And so this is, we can do the similar thing. And then MgO is 5%. And then oxygen. Then we can have the more realistic phase diagram, which is similar to the converter slag. Okay. And here, I mean, I just mentioned that also C2S saturation and the monoxide saturation. Monoxide in this case is MgO plus ion solid solution. Okay, so let's try to do this quaternary phase diagram calculation. Okay, so let's go to my backstage. So let's just close this one, previous calculation. Close it. Yes. Oh, no, sorry. I'm not going to save it, so it's okay. Now go to the phase diagram. New. Okay. So now I'm selecting all these 4. CaO, SiO2, FeO, and MgO. So the one you want to actually pick the constant value should be in the quaternary phase diagram. The one you want to actually pick the constant should be the last one among the 4. Okay, and ion. You can put the ion in the very first if you like. That's also possible. But we can put the ion in the very last also. And then like this, and database search. So PECT-PS, FT oxide. I don't care about this one at the moment. Only these 2. Say okay, and then go next. And then select all the solution phase, solid phase, liquid phase if you like. And you can select all of them, or you can select only ion if you like. But I mean, I'm intentionally remove the old oxide phase, for example, magnesium, silicon, calcium, and iron. Doesn't matter. Say okay. And then go to variable. Left click. I'm doing triangle calculation, triangle phase diagram calculation. And the composition 3, 1, or in this case, I'm going to pick the ion amount. So 4, 0. Okay, set next. And then temperature 1650 degrees Celsius as we did before. And then here now you say A, B, C axis. So first 3 is automatically set as A, B, C condition. I'm sorry, if you want to actually use this ion saturation with additional ion amount, you have to actually put the ion as a very last. I'm sorry about that, because otherwise you're going to have this one as the first one, and which doesn't make sense. Okay, so ion should be the last one in this case. So A, B, C, so 1. So A corner, I want to use SiO2 as A corner. Okay, and then go next. And B corner, I want to use the C corner. This is C corner. I want to use the ion oxide as C corner. And then third one, I want to use the CaO as B corner, and then this one 5 cent, 0.05. And of course here you can use also 100, yeah, and everything you can use 100, then it should be weight cent. Okay, go next. And Fe, so it's very small amount, 1e minus 6, for example, something like this value. Okay, very small amount. So it's not really the so if it's very small amount, it means it's very close to the oxide system. If you add a lot of the amount of the ion, then you are somewhere in the middle of the oxide system and the metallic system. Or if you add extremely high amount of ion, then you'll have almost pure ion with a very small amount of the slag system. So that's also possible, but that's not what you want to actually calculate. Okay? Say okay. And then do the calculation. And we are doing this calculation. Sometimes probably you may interest how does what kind of algorithm we are using for the phase time calculation, and we say that the zero fraction line calculation. And if you look at one of reference in the fact stage, you can find out what's the amount, what's the actual meaning of the zero phase fraction calculation, and that's written by the Pelton. So if you have time, please go and look at it. Okay, so now let's say this label mode and then click, then you can see that this is liquid ion plus slag phase, and then this is liquid ion with a slag and the Ca2SiO4, and then again this is monoxide plus slag phase, and etc. And this is SiO2 plus slag phase. So this is single slag phase area, so this is dicalcium silicate saturation region, and this is slag which is saturated with the monoxide. So in terms of the dephosphorization, I mean, you should make a reasonable amount of slag with a high FeO. So somewhere here is very good, and with a high CaO condition. So here, and because this is, if you're above this one, you have the monoxide forming, and this monoxide is the FeO and MnO. No, in this case, MgO and FeO actually the third solution. And so if you have refractory, you have to also look at this one very carefully, because this line, if your slag composition is not saturated with this one, then you'll dissolve a lot of your refractory MgO, and then the slag will automatically go to the saturation to this side. Okay, then you have the huge loss of your refractory material. Okay, that's good. So this is one of the way, and I'll show you one other way to set it. Okay. The other way you can set is, okay, let's go to the same thing, and instead of 4, so I'll say 3, 1, and then go next. Same thing, but here I'm going to set ion activity of liquid as 0. That means log activity of ion equal to 0. It means activity of ion liquid equal to 1. Okay, and then we do the same setting. So here, here, here. Okay, everything is same, and then say okay, and then calculate. So it means I intentionally ask to the fact stage, don't add ion metal as 0.001 or 10 to the minus 6 gram. I'm asking to the fact stage, you add ion by yourself, but don't make liquid ion, just make actually the activity of ion equal to 1. So it means the ion amount is 0, but the activity equal to 1. So it's ion saturation condition. And the result will be almost same. So as you can see here, I mean, the result is, I mean, you cannot even distinguish the result from here, this calculation with the previous calculation. It's exactly the same type of calculation, but in this case, activity of ion liquid equal to 1. Okay, so you can now you see that there's no liquid Fe, something like this, because the activity is just fixed, so there's no amount. Okay, so this is also one of way. we can set the ion saturation condition. Okay, so I think this is the interesting actual calculation. And one last thing I want to show you is the close it. So sometimes you want to do the calculation for the CAO, for example, Liquidus projection. So liquid projection means we are collecting all the liquid part and then make a Liquidus line and then project all together into the one diagram. That's the Liquidus projection. If you go to the very first actually the presentation of this whole lecture, then you can see actually the fundamental engineering thermodynamics 101, and then I explain a little bit about Liquidus projection for the ternary system. So let's look at one simple system. So for example, let's say new reaction, say yes, yes, and let's take CaO, Al2O3, MgO, ternary system, okay? And then database search, I'm not taking packed PS, only FT oxide. And you can use also packed PS as well, but at the moment, let me just take it simply FT oxide, because this is oxide system only. And unit, I'll just leave it as a gram, and then go next. And then you select all the possible phase, which is suggested by this one. And then in order to activate Liquidus projection, then you have to do this special, actually the treatment here. So on top of this slag, so in this case, the liquid is the slag, okay? So Liquidus projection, you have to set which one is the target phase. And so in this case, slag is liquid. So we have to use the slag as a target phase and go mouse right click. And then you'll have option here. You just move a little bit here and go here, mouse right click. Then you can see the only plot this single phase. Can you see it? Only plot this single phase. You click this one, then it means we are ready for the for actually the calculate Liquidus line. Okay, that's what it means. And then go to the variable and then ternary phase diagram next. And then instead of fix the temperature, now go here, say projection. So this is Liquidus projection. So every 100 degree. So you don't have to worry about this, define the minimum maximum. But if you want to calculate Liquidus projection from 1400 degree to 1600 degree only, then you can define here minimum maximum. But otherwise, if you just only select how, what kind of the step you want to do the calculation. So every 100 degree calculation, Liquidus line, for example, 1000 degree, 1100 degree, 1200 degree, something like this. Okay, every 100 degree Celsius in this case. And then you can, the factor you will find even minimum and maximum by itself. Okay, and then you set your axis. So I'll set Al2O3 as A, and good, C as MgO, good, and CaO on the B corner here. That's good. Say okay. And then once you do this kind of the calculation for the projection calculation, sorry, then you can have this option is showing up also. So univariant line. Are you going to also see the univariant line and the isothermal calculation as well? Isotherm is the Liquidus line, every 100 degree Liquidus line. That's the isotherm. Univariant line was the phase boundary for the primary solid phase. So it's kind of the, in the phase, in the projection, Liquidus projection, we see some phase area and then between the boundaries. So it's a kind of valley in the mountain. That's the univariant line. And then if you click, then FactSage will do this. Will do the very interesting calculation for you. So here you see FactSage first calculate all the univariant line, because it will change the temperature and then it will try to find where's the two phase region at each temperature, because that's the phase boundary. Liquid plus two solid phase boundary. And that's the univariant line in each temperature. Okay, so it will find all of them, and then it will start the thermodynamic calculation. Okay, sometimes it takes a little bit long But I mean, you can, in this case, it's a relatively simple phase diagram, so it'll be okay. But sometimes it takes a little bit long time, so then you can just leave the actual calculation and then come back from the copy break. Then you're going to see the result. And you can do this kind of liquid projection, not only ternary system, you can do the multi-component system. So as we did before, so you have 3 component plus 4th component, you can pick the constant value, and then you can do this kind of calculation. Okay, then it will give all the liquid projection in the quaternary system as well. So when I was the PhD student in the about year 2000, I did all this Liquidus calculation one by one, line by line, literally. And for example, in order to get this ternary phase diagram, I mean, this is one of my, I wrote the paper about thermodynamic modeling of the CaO, Al2O3, MgO ternary system here. And for me, when I did the calculation one by line in the year about 2000, it take about let's say 1 hour easily to calculate all this actual phase diagram. But now within the about 3 minutes, you can get the phase diagram. Okay, so here all this line, as you can see, this is isosome line. So at the given temperature Liquidus line, you can see 2700 degrees, 2600 and etc. And then here you can see actually the phase name, so monoxide. Instead of here and here, it's in the middle because this side is the monoxide and this side is also monoxide. So CaO rich monoxide, MgO rich monoxide. Okay, and then here you have spinel phase, and there's the many small phase, and then Al2O3 phase, CaO, Al2O4 phase, CaAl2O4 phase, and etc. So all of this one. And so this we call it univariant line, isosome. Okay, both of them is shown here. And then also, if you look at all this one, 1, 2, 3, 4, 5, 12 here, so you can see the small number here. So let's just make it a little bit big. So if you look at it here, number 7, number 6, and number 4, all this one is so-called invariant reaction point. So like ternary eutectic temperature, ternary peritectic temperature, and all those kind of things. And those 1, 2, 3, 4 is corresponding to those univariant reaction point. And so, for example, at number 7 here, number 7, you see CaAl2O4 and CaAl2O4, CaAl4O7, and spinel. So here, left side, CaAl2O4, CaAl4O7, and then spinel. So this means it's a univariant line, the invariant point from liquid become 3 phase. Liquid become these three solid phase. Unfortunately, fact it doesn't tell you whether this is the ternary eutectic point or ternary peritectic point. You have to actually look at it, look at the phase diagram by yourself, and you have to decide whether it's ternary eutectic or ternary peritectic. Or if you do the small calculation here around this composition, and if you cool it down, you can see that Liquidus line is continuously going down. After passing number 7, then it means ternary peritectic. And if the Liquidus, if you cool it down at the decomposition, and then if the liquid is just disappearing after 0.7 here, then it means it's a ternary eutectic point. So you can actually look at those kind of trick in the equilibrium calculation to find out whether this is peritectic or eutectic point. Okay. And also same time, if you look at this one, number 7, this is composition. So A, B, C composition, A, B, C composition here in the phase diagram. And so this is composition of liquid phase. So number 7 composition here. That is this composition. And then when is the number 7 reaction is happening is at this temperature, 1522.77 Celsius. You will have this plus liquid is coexisting, and then it will make invariant reaction. That's what it means. Okay. So if you look at all these temperature, you can easily find what is the lowest temperature. So for example, number 12 have the lowest temperature. Yeah, this should be at least ternary eutectic point. Okay, and then you can also look at all the other actually invariant reaction in this way. Okay, so how to actually understand the ternary phase diagram or ternary Liquidus projection, that actually can be seen from the my first lecture about engineering thermodynamics 101. Then you can understand basically what is this kind of ternary phase diagram means. Okay, so this is the ternary projection calculation. Okay, so thank you very much.